Hello again. Today I want to talk about harmonic excitation and the concept of beat period. Here we have a mass spring system with no friction, no damping, subjected to a harmonic force. So this force, f of t, has some amplitude f0, and it's harmonic. So let's say we have a cosine wave, cosine omega dr. Here omega dr is the driving frequency or the input frequency. So this mass is excited by this force, and we want to actually find x as a function of time, the motion of this mass m. Okay, so what we're going to do, I'm going to actually get the differential equation and show you the solution to it. I'm not going to go through the derivation of it and how I get the solution, but then I want to talk about, look at the solution and tell you about talk about the beat period and the beat phenomenon. Okay, so the differential equation of this system is obviously mx double dot, that's mass times acceleration, plus the force of the spring kx equal to the applied force f of t. Now remember, f of t, rewrite it over here, mx double dot, just erase this for a second. So we have mx double dot plus kx, and remember the force has some amplitude f0, cosine omega drt. So remember, the system has its own natural frequency. The natural frequency of the system, omega n, is the square root of k over m. So now if we go ahead and divide everything by mass, basically that's called the normalization. So we end up getting the differential equation becomes x double dot plus omega n squared, the natural frequency squared, times x, equal. Now this ratio of f0 over m, then we're going to call it lowercase f0, and this is called the normalized amplitude. So this now becomes f0 cosine omega drt. So now the question is, what is the solution to this differential equation here? Now we are going to assume that the initial conditions are 0, meaning that initial velocity is equal to 0 and initial position equals 0. So at t equals 0, the initial position is 0, and initial velocity, which is the x dot, is equal to 0, since this is subjected obviously to a force. So this is obviously second order differential equation that is not homogeneous because of the force acting on the system. So the right hand side is not equal to 0. The solution to this is going to be x as a function of time, the motion of the mass as a function of time. It's going to be this normalized amplitude f0 divided by omega n squared minus omega dr squared. Remember, omega dr is the driving frequency, times cosine omega dr t minus cosine omega nt. So remember, this is the solution, the response of the system or the motion of the mass if the initial conditions are equal to 0. Now, we can put this using trig identities. Let me go to the next page, in a much better form so we can really see what's going on. So using a trig identity, that solution in the last page turns into a 2f0 divided by omega n squared minus omega dr squared times two sine waves now. One sine wave with the difference between omega n and omega dr divided by 2, of course, times t, and then another sine wave with the sum of the two omegas divided by 2 also times t. So now look, we have two sine waves, one riding on over the other sine wave. So now let's talk about the beat phenomenon. What happens when, when does beat happen? The beat phenomenon. Well, it happens if omega dr, the driving frequency or input frequency, is very close to the natural frequency of the system, which is the omega n. So, for example, I have done a simulation based on the fact that the mass of the system is, say, 1 kilogram. The stiffness, let's say, 16 newtons per meter. So right away we can go ahead and calculate the omega n. Omega n is the square root of k over m. So that becomes 4 radians per second. Now, what if I make my omega dr to be very close to this, 3.9 radians per second? That's when the beat happens. So what will happen is that you see this difference between omega n minus omega dr. Imagine if you had a 4 here and a 3.9 here. That becomes very small after you divide it by 2. And then the other frequency actually becomes large when you add 4 and 3.9. So what will happen if you try to find the period, the frequency that is small is going to have a larger period than the one that has a large frequency is going to have a smaller period. So we're going to have two sine waves, one with the large period and one with a small period. So what will happen is that since t, the period, I mean, I'm going to call it the beat period now with using the subscript b, is going to be 2 pi because we have to change from radians per second to seconds per cycle, divided by this frequency here, omega n minus omega dr divided by 2. So this becomes actually 4 pi divided by omega n minus omega dr. So what would be that for our example? It's going to be 4 pi divided by, remember omega n is 4, and we have 3.9 here. That's about 125.7 roughly seconds per cycle. So this is the beat period. And the other frequency actually, the other beat is going to be a little bit, much smaller because we are taking 2 pi and we're dividing by the sum now of the omega n over omega dr, omega n plus omega dr divided by 2. And this actually becomes 4 pi divided by omega n plus omega dr. So this is going to be smaller. So let me show you now the picture in the next page. Look, this is an example here. The mass is 1 kilogram. And the stiffness, as I said, is 16 newtons per meter. And look what happened. One beat period is from here to here. That's your T sub B, which is actually 125, about 125.7. So you see a small sine waves, and these are small sine waves like this. They build up, and then they diminish eventually. And you will have something like this as shown in the picture. So now the other period is between peak to peak. Let me erase this. So peak to peak of right here. So that's the other 4 pi over omega n plus omega dr. That's the smaller period. So this concept, this is known as the beat period, and only happens when the frequency, the input frequency of the system, and it doesn't matter if it's a cosine wave or sine wave, the input frequency, the omega dr, is very close to natural frequency of the system. Remember the example of 4 radians per second of the natural frequency, and the driving frequency was 3.9. Okay, in the next video I'll talk about resonance. What happens when the driving frequency is exactly the same as natural frequency, and that means resonance. Thank you for listening.